Hi. I'm Nir Mandelker. I'm a student working with Avishai Dekel at Hebrew University. I'll be continuing this discussion about giant clumps, specifically clumps in the simulations and how we can predict observable signatures in actual real galaxies. So, oh, this is not working. So, certainly after the last couple of talks, I think it's safe to say that the only thing we can be sure that we know about clumpy disks is that they exist at redshift 2. A lot of them exist at redshift 2, and the simulations seem to be producing these clumpy disks in an extremely robust way. These are two observed galaxies. These are two of our simulated galaxies using the ART simulations that Shigeki discussed, and I'll discuss further. And this, I don't think there's anybody who could possibly say that this is not robust both in observations and in simulations. However, there are a lot of things that we think we know about clumpy disks, so we thought we knew about the clumpy disks. We thought that high gas fractions cause giant clumps to form in situ in the disk through VDI because of the Toomre Q parameter, but is it really Toomre? We heard nice talks by Andy, by Shigeki. We'll hear another talk tomorrow by Avishai that we're no longer sure that it's the simple case that we thought. And another option is that, well, a lot of these clumpy disks could just be merging systems. There's still a lot of people who see images of clumpy disks on the sky and go, this must be a merging system. Another thing we know, or we think we know, that clumps should survive feedback, migrate to the center and merge with a bulge, help in bulge formation. But we also know that clumps should not survive feedback, and they should disrupt in a much more shorter time. So what would we like to know about clumpy disks if we could get everything that we wanted? Well, perhaps the most basic observational question is, what is the fraction of clumpy disks as a function of disk mass and disk redshift? Yicheng will discuss that in the observations in the next talk. We would also like to know how many of the clumps were formed through VDI, and more fundamentally, physically, what is indeed the origin of the instability? Can these in situ clumps be distinguished from the ex situ clumps, from the mergers? And also we want to know, do the clumps indeed survive feedback, and are they able to migrate to the disk center, or do they very rapidly disrupt? For the bulk of my talk, I'll be focusing on these last two questions, and if I have a couple minutes at the end, I'll address these in the simulations, which Yicheng will follow up on. So why is this even an interesting question, clump survival? Why is it not converged? This is from old simulations by Daniel Severino, 2010, what we call the Generation 1 hydro-art simulations. The resolution is about 50 parsec. It's only supernova feedback, thermal supernova feedback. And you can see here that clumps do migrate to the center in about 250 million years in orbital timescale, and they all merge and coalesce at the bulge. A couple years later, there were these simulations by Shai Ganel et al. Using the Gadget 2, where he put in artificial subgrid recipe for strong winds, and he sees that when he turns the winds on, the clumps basically disappear. And that was evidence that it was all perfectly consistent with observations that the clumps should not survive. Well, we wanted to think about this kind of in a more fundamental way. We wanted a very simple toy model, and our favorite simple toy model is always the bathtub model. So we wanted a bathtub model for clump evolution, which basically says that the change in the gas mass and the stellar mass in a clump is just an equilibrium between accretion, star formation rate, and clump outflows due to feedback, and we also allow for the stars to be removed by tidal stripping. And I want to go through very briefly the main aspects of this very simple model to see what they mean. I am going to be assuming here that Q is equal to 1. That doesn't necessarily mean that the clumps had to have necessarily formed through the typical Toomre instability. I'm not going to discuss that right now, but we're talking about the massive clumps which do exist, and I'm assuming they exist in a Q equals 1 disk, and that has various important implications. For one thing, you can calculate the migration time to the center. You can do it any way you want. The dynamical friction, torques, clumping counters, it doesn't matter. You always get the same answer. It should be about 10 dynamical time scales with this parameter delta that Andy mentioned. You can also do a very simple way of calculating the mass gain onto clumps. The simplest thing you could do is a cross-section argument where this parameter alpha, in a way, represents the mass fraction of the gas that is actually bound to the clump that's going to cross the cross section. And if you do the calculations, it turns out that the accretion time is more or less equal to the migration time. If that's all there is, if there are no strong outflows, then this alone will tell you that the clumps should at least double their mass in a migration time before they hit the bulge. And this was indeed what we found in a paper last year where we examined these weak feedback simulations. Clumps grew in mass as they edged closer to the center. This is the distance from the center. This is the mass of the clump. Black represents in situ clumps. And they about triple their mass during their migration, as you would predict just from this. Another thing you have to include in the model is the star formation, and you can assume, typical parameters for star formation and for the clump over density, and this works out to be about a little longer than the migration time scale. And the most important new aspect that we do have to account for is the feedback, is the outflows, and so this is basically based on these three works, Deckel and Krumholtz 2014, which is based on Krumholtz and Thompson 2012 or 2013. I'm not going to go into all the details because it's extremely complex, but the basic thing is that you get a steady wind with minimal photon trapping because the winds basically become destabilized and you only get a boost factor of 2 or 3, which leads to mass loading factors of about 1 or 2 from the clump, which is perfectly consistent with observations of outflows from clumps. If I assume this, then the outflow time scale is also slightly longer than the migration time scale. And the bottom line is that the migration time scale is approximately equal to the mass doubling time, which is shorter than the outflow time, which is shorter than the star formation rate time. This alone tells me to an order of magnitude, clumps should survive until they reach the center. But I didn't want to assume that. And I took this model and I plugged it in and I plugged it into a computer. And as a function of the mass loading factor, where I assume these typical values for the other parameters, you find that at any mass loading factor, the mass varies by less than a factor of 2 during the migration. In fact, the mass is basically constant for very typical values of the mass loading factor. If eta is much smaller than 1, the mass grows by a factor of 2. If eta is much larger than 1, indeed the mass will go to 0. In fact, for most values of the mass loading factor, the gas fraction seems to remain more or less constant. I'm sorry, I didn't say this is a function of the mass loading. This is the final value over the at the end of migration divided by the initial value when the clump forms at the outside of the disk. And pay attention to the magenta, which is the total baryonic mass in the clump. The green is the gas fraction. You can see that there's very small variation for most typical values of the mass loading. We didn't want to, so we have the analytical toy model of prediction. The next thing we did is ask our friend Frédéric Bourneau to look at his simulations of isolated disk galaxies that Shigeki mentioned, and we followed clumps that were above 10 to the 8 solar masses that survived in simulations for longer than 200 million years. We ran he ran two sets of simulations with radiation pressure and without radiation pressure. And you can see that without radiation pressure, the clump mass continues to grow. With radiation pressure, it basically caps off at a finite mass. The gas fraction goes down in both of them, but it saturates at a slightly higher value with RP, and this is all inconsistent with the predictions of the toy model. The next thing we did after the isolated case is let's go to the most complex nonlinear case. Let's go to the cosmological simulations, which is supposed to represent the real universe, and see what we can find there. So I'm dealing with 30 pairs of simulations with identical initial conditions run by Daniel Severino, the ART code. Halo masses of 10 to the 11 to 10 to the 12 at a redshift of 1, AMR resolution of 25 parsecs. 2 pairs of simulations were run, one with and without radiation pressure. The current simulations have a boost factor of just 1. We're now in the process of running new simulations with a higher boost factor. I find clumps in 3D, in gas and stars, and I track the clumps based on their stellar particles. So before I tell you what actually happens, I want to proof by pretty pictures just to see two pictures of simulations with only supernova feedback and the supernova plus radiative feedback. You can see here these clumps, which are very massive. I won't tell you their exact masses, but they basically survive. But if I go to another example where a lot of these clumps are much lower in mass, they're all gone. And I'm left only with the massive clumps. If you didn't believe the pretty pictures, you can look at the mass function that you get for off-center in situ clumps. Blue is without radiation pressure, red is with radiation pressure. You can see that small clumps disrupt, the giant clumps survive. Incidentally, the Toomre mass is predicted to be about here, and as Andy said, the Toomre mass is basically near the tip of the mass function. But I want to zoom in on the mass function, and you can actually fit quite nicely power laws to this massive end, and I haven't really looked into exactly what you can say, but this is at least consistent with the mass function of GMCs in the Milky Way. So I measure the typical values in the simulations for the parameters of the model, and I put them into the model, and these are the predictions you get. Again, magenta is going to be the baryonic mass, green is going to be the gas fraction, this time as a function of time normalized to the initial value. The solid line is including RP, the dashed lines are not including RP, and this is what I get for the simulations for the mass and for the gas fraction. The solid black line is the median of the population. All the thin colored lines are all the various clumps that I found, and the evolution is quite consistent, and indeed the mass remains basically constant. Without RP, it does tend to grow quite a bit. The other interesting thing, you can see that while the gas fraction in the median here is very consistent with the shape of this, with RP, you get a lot of clumps that momentarily lose all their gas and then accrete their gas back again, which you don't see in the simulations without strong feedback. The last thing in this respect, what observable signatures would this produce? Well, the gradients of the massive clumps. So this is again just looking at the massive clumps above 10 to the 8 solar masses as a function of their distance from the center. We have mass, age, and the specific star formation rate. And you can see that in situ clumps, which are in black, as they get closer to the disk center, they become older. And with lower specific star formation rate, the age gradient is much steeper than the background disk, which you can see here in blue, which shows that they must have evolved separately from the underlying stellar population in the disk. But you get only a very, very weak mass gradient because on average these clumps are supposed to have basically constant mass as they migrate. The ex situ clumps, which are just little mergers, I can identify them through either dark matter or through where their stars were formed. Their gradients are much, much, much weaker. They're basically constant. They're much older. They're much more massive, and they have lower specific star formation rates, and they should appear redder in the observations. These gradients have been observed by Natasha Foster-Schreiber and Yicheng Guo in these two papers, and these seems very consistent with the picture that we're saying that clumps survive, the massive clumps survive, and they migrate to the center. I'm out of time, so I'll just tell you that about half the mass of the clumps is actually not in situ clumps, but in ex situ mergers. About a third of the star formation rate, even though in terms of the number, they're a small fraction of the population. This is the clumpy fraction. Here I'm basically only looking at clumps that are more massive than 1% of the disk mass. Here I'm only looking at clumps whose star formation rate is more than 1% of the disk star formation rate. You'll notice that the values here are higher than they are here. This is the fraction of clumpy disks. This goes in the direction of what Andy was saying, that a lot of the star formation rate is going to be in lower mass clumps and not in higher mass clumps. This is still a work in progress, and you can compare this to observations of clumps by Yicheng Guo, and the numbers are quite consistent. About half the galaxies in any given mass or redshift are going to be clumpy. And I'm out of time, so this is just my summary. In situ giant clumps and transient features form, ex situ clumps merge, small clumps disrupt, the massive clumps survive with a steady wind, gradients in age and color due to migration and accretion, no mass gradient. Ex situ clumps are a minority in terms of number, but a majority in terms of they're a significant population in terms of star formation rate and mass. In situ clumps are younger, higher specific star formation rate, and higher gas fractions. They're bluer. Half the galaxies are clumpy with about a third of star formation rate in the clumps. Thank you very much for your attention. and I'll take questions. So I was only focusing here on the larger ones.
Right.
Yeah.
Do you have a sense, I mean, if you're 50% ex situ, do you think that holds with the Canvas observations?
So the 50% was in terms of mass. So if I look at only the clumps that are more massive than 10 to the 8 solar masses, which was my threshold here, then half the mass of clumps above 10 to the 8 is in ex situ clumps. But again, they're only about 10 or 15% in terms of the number. They're just individually much more massive. So yeah.
I don't know, what's wrong with the analogy of thinking of clumps as little galaxies in terms of galaxy formation? Right, so I know they don't have dark matter, et cetera, but you have a potential around 50 kilometers a second depth, it's about the right size. Then if you kind of generalize to what galaxy formation simulations are telling us for those galaxies, they expect pretty high mass loading factor, and then a lot of the mass being sent out of the galaxy, and
well,
those kind of mass factors would disrupt your clumps. And so I'm having difficulty understanding how to put together the formation of 50 or 60 or 70 kilometer a second galaxies, where everyone tells us that the outflow should be very effective, and the clumps, which is in the same potential depth, about the same size, about the same gas mass, where you're saying the outflow shouldn't be particularly effective.
well, for one thing, it's a lot more difficult to drive a strong outflow into the disk. These clumps are basically embedded within a much dense, a lot of gas, very dense disk. The outflows do preferentially go perpendicular to the disk. And you could argue that if I do put in stronger feedback, the mass loading factors will be higher. That, I mean, we are currently in the process of testing simulations with higher feedback. I mean,
There's a huge difference in mean density.
Yeah.
Right? These clumps have mean densities
Of course.
10 to the 3, whereas the galaxies you're talking about with the same potential level have mean densities of 10 to -1.
Yeah.
Right. There's a huge difference in how energy dissipates if I try and drop a shock into something at a mean density of 10 to the 2 and something at a mean density. So that's the difference. I mean, like, if you set off a supernova in a galaxy with a density of 10 to the -1, if you set off gamma rays, it's huge, it loses no energy in radiation.
Phil and Warren Murray telling me that you've already evacuated some very nice gas to radiation in the by the time.
Where is the
Well, I don't know if you believe it.
View.
Yeah, we should continue this later. So let's thank Nir again.
We know about clumpy disks, so we thought we knew about the clumpy disks. We thought that high gas fractions cause giant clumps to form in situ in the disk through VDI because of the Toomre Q parameter, but is it really Toomre? We heard nice talks by Andy, by Shigeki. We'll hear another talk tomorrow by Avishai that we're no longer sure that it's the simple case that we thought. And another option is that, well, a lot of these clumpy disks could just be merging systems. There's still a lot of people who see images of clumpy disks on the sky and go, this must be a merging system. Another thing we know, or we think we know, that clumps should survive feedback, migrate to the center. Hi. I'm Nir Mandelker. I'm a student working with Avishai Dekel at Hebrew University. I'll be continuing this discussion about giant clumps, specifically clumps in the simulations and how we can predict observable signatures in actual real galaxies. So, this is not working. So, and also we want to know, do the clumps indeed survive feedback, and are they able to migrate to the disk center, or do they very rapidly disrupt? For the bulk of my talk, I'll be focusing on these last two questions, and if I have a couple minutes at the end, I'll address these in the simulations, which Yiching will follow up on. So why is this even an interesting question, clump survival? Why is it not converged? This is from old simulations by Daniel Severino, 2010, what we call the Generation 1 hydro-art simulations. The resolution is about 50 parsec. It's only supernova feedback, thermal supernova feedback. And you can see here that clumps do mine. Only after the last couple of talks, I think it's safe to say that the only thing we can be sure that we know about clumpy disks is that they exist at redshift 2. A lot of them exist at redshift 2, and the simulations seem to be producing these clumpy disks in an extremely robust way. These are two observed galaxies. These are two of our simulated galaxies using the ART simulations that Shigeki discussed, and I'll discuss further. And this, I don't think there's anybody who could possibly say that this is not robust both in observations and in simulations. However, there are a lot of things that we think are merge with a bulge, open bulge formation, but we also know that clumps should not survive feedback and they should disrupt in a much more shorter time. So what would we like to know about clumpy disks if we could get everything that we wanted? Well, perhaps the most basic observational question is what is the fraction of clumpy disks as a function of disk mass and disk redshift? Yicheng will discuss that in the observations in the next talk. We would also like to know how many of the clumps were formed through VDI, and more fundamentally, physically, what is indeed the origin of the instability? Can these in situ clumps be distinguished from the ex situ clumps, from the mergers?